Good morning. Today we're going to continue with our talks on probability, and this is section 12.2. And there are a few vocabulary things to begin with. So the first one is something called independent events, and that's where one outcome has no effect on the next. So for example, if I'm rolling a pair of dice and I see a 3 and a 4 come up, and I pick up the dice again and I roll those dice, getting a 3 and a 4 on the first time doesn't affect what happens the second time I roll the dice. Whatever's going to happen is going to happen. The 3 and the 4 meant nothing compared to my next roll. Whereas when they're dependent, which is the next phrase, that would be, for example, if I have a deck of 52 cards, a normal playing deck of cards, and I say, Yannick, pick a card, and he draws out the Jack of Diamonds. And I say, you hold on to that card, Yannick. And I go over to Caroline, and I say, Caroline, pick a card. The probability of Yannick picking a diamond was a 1 in 13 chance. But now, because one card has been removed from the deck, when I ask Caroline to draw a card, that card that she picks is no longer a 1 in 4 chance, I should have said, is no longer a 1 in 4 chance. It's a 12 out of 52, a 51 chance, because there's only 51 cards left on the deck, not 52, and now there are only 12 diamonds. That's called dependent. So for the next one, dependent probability is when one event probability is affected by the previous event. Conditional probability looks like this. This is how they write it. P parentheses A/B, and it means the probability of A occurring given that B has happened. And we'll talk more about that later. I'm going to show you something called the Monty Hall problem. So a more practical application maybe, or example would be, for if I said, what's the probability that I picked a girl out of a crowd knowing that that person had long hair? Okay, so this is the probability that you know that you have a girl if you pick a person at random and they had long hair. When you're doing this probability stuff, sometimes a tree diagram is a very good way to see things. So in this next problem, they tell you that there's a 30% chance that you're going to wear your Uggs to school on any given day. And based on some of the things I see, that's true. And there's a 25% chance that your friend's going to wear hers. And so what's the chance that you both wear them on the same day? So what happens is, like if you look at what's going on, you will see, first of all, if we just talk about you, there is a 30% chance, which remember we can write as decimals, percentages, or fractions. So I'm going to write it as a decimal, 0.30, that you do wear your Uggs. And there's a 70% chance that you don't. And then if we look at your friend, if you wear your Uggs, your friend has a 25% chance of wearing her Uggs, but a 75% chance of not. And if you don't wear your Uggs, your friend's probability is not affected. So your friend still has a 25% chance of wearing her Uggs and a 75% chance of not. And this is called a tree diagram. So you are in the pink, and that's what you do, and then your friend may or may not, whether you do or do not, wear yours. And the question is, what's the chance that you both wear them on the same day? And what that means is you're looking for the path that says you wear yours and she wears hers. So when you have these things and you're talking about probabilities, in order to find the ending probability, you will multiply the two probabilities because they're independent events. So you take the 0.30, which was the probability of you wearing your Uggs, times the 0.25, which was the probability of her wearing her Uggs. And when you multiply those two things, there's a .075 chance that both of you will wear your Uggs on the same day. You could also write that as a 7.5% if you wish. If you're trying to find the likelihood that at least one of you wears them, what that means is you wear them or your friend wears them. And so there are actually a couple of different possibilities for that. For example, as I look at these different paths, you could both wear them, which was that 0.30 times 0.25, because it says at least one of you wears them. There is the possibility that you wear them and your friend does not, which is the 0.30 times the 0.75 situation. And there's the possibility that you do not wear them and your friend wears them, which is the 0.70 times the 0.25 situation. There are three cases where at least one of you is wearing them. Both wear them, you wear them, she wears them. When that occurs, you multiply each of the pieces for you and your friend, but then since there are three possibilities, you add those up together. And when you add those up together, I believe that you're going to get 0.475, or in other words, a 47.5% chance that that's going to occur. So the last part C in this particular problem says, what's the chance that neither of you wear them? That's the highlight in red. You don't wear them, 70%. She doesn't wear them, 75%. So then you would say, oh, okay, that means 0.70 for me not wearing them, 0.75 she doesn't wear them, and that's a total of 0.525, or 52.5%. And you could have got this, another way to get this is, you could have just gone 1 minus the 0.475. And 1 is representing 100% chance that something's going to happen. Take away whatever did happen from before. So there are two ways to think about it, and you can choose either way. Both are good. Okay, so in this last example on this slide, you're picking cards out of a deck. We were talking about that earlier with Yannick and Caroline. And without replacement. The phrase without replacement means once you take something out, it stays out. You're hoping to get all 4 5s. And so what's the likelihood that that's going to occur? So what happens is in a normal deck, you may or may not know that there are 52 cards total. So when you're drawing a card out of the deck, what's the chances that you get a 5 when you draw a card? There are 4 5s out of the 52 cards. That's your probability of getting the first 5. But then you take a 5 out. How many cards are left over?
51.
51. And how many 5s are left? 3. So your likelihood of getting that next 5 is 3 out of 51. And then there are 2 5s left over, and there are only 50 cards left over. And then, to get that last 5, there's only 1 in the whole deck, and there are 49 cards left over. And what you would do in order to find out your likelihood of this happening is you would take and multiply those fractions together. So if I do that, it's a very small number, I'm sure. 4 times 3 times 2 times 1 divided by 52 times 51 in parentheses times 50 times 49. And I get this thing. 0.0000037 to the nearest 2 non-zero decimals. Now on my calculator, I actually saw something that said 3.69 with an E. I saw this thing, 3.69 E minus 6. What that's telling you is wherever your decimal place is, move it 6 places to the left. So if you're moving the decimal 6 places to the left, that means there's going to be 5 zeros and then the rest of the number. And so I rounded the 6 to a 7 because the 9 said go up. All right, in this next problem, number 3 example, it says we have a recipe and there are 4 ingredients.